Good evening, everyone. I hope I'm audible. Welcome to the week 10 live interaction session for the course on Renewable Energy Engineering, Solar, Wind, and Biomass Energy System. Let's just wait for a few minutes for others to join before we begin our session for today. I hope I am audible to you all. So let's just start our session for today. Let me just present my screen. I hope my screen is visible. Can you please just confirm whether my screen is visible?
Yes, sir. It is visible.
So it's visible, right? Okay, so let's just start our session today. I welcome you all for the week 10 live interaction session for the course on Renewable Energy Engineering, Solar, Wind and Biomass Energy Systems. Myself Pratyumnan, a PhD scholar at the Indian Institute of Technology, is a course team member responsible for conducting the weekly live interaction session. This course is offered by Professor Vaibhav Vishant Gaut sir and Professor Anandalakshmi ma'am from the Department of Chemical Engineering, Indian Institute of Technology, Guwahati, under the NPTEL program. So in the week 9 live interaction session, we focused on understanding the combustion process and the torrefaction process. So how is the so what is actually the torrefaction process and how it is similar to the carbonization and the pyrolysis process, and how it is different from the carbonization and the pyrolysis process. We also saw the ways to calculate the air fuel ratio, their importance, the equivalent ratio, and its importance of what it actually signifies when your equivalence ratio is less than 1, equal to 1, and greater than 1. So if you are able to recollect of what we discussed in the previous live interaction, if the value of phi, that is your equivalence ratio, is less than 1, then it is called as a lean mixture or fuel lean mixture, where the fraction of the fuel in the air fuel mixture is going to be less. If it is greater, then it's a fuel rich mixture. If it is equal to 1, then it maintains a stoichiometric ratio. And also we discussed a numerical problem, to be honest a very detailed numerical problem on, if suppose if I have a particular requirement to power my house or power certain equipment or power a particular application of this much power, let's say of some x amount of power, then how much amount of or how much amount of biogas or biomass I need to feed into my digester so that I can supply this much amount of power to my house or whatever application it is. So we did the reverse calculation from knowing what is the power requirement towards calculating how much amount of the biomass needs to be fed into my digester for the power generation purpose. And also we solved some numerical problems on calculating the air fuel ratio, how to develop the combustion equation for a particular hydrocarbon when it is given, like methane, ethane, propane or butane or decane. If any kind of hydrocarbon is given, how to develop or what is actually the combustion equation, both in when the hydrocarbon is burnt with the stoichiometric quantity of air or when it is burnt with the excess quantity of air. So this is what we saw in the last week live interaction session, as well as in the NPTEL course also. Till last week we came up till that point. So in the biomass conversion process, there are two more processes which is left out, which is the gasification and the pyrolysis. So these two processes are meant to be covered for the week 10 live interaction session, and we will be focusing on that now. So this is the, so let us start with the gasification process. If you remember, both in week 9 and if I am not wrong in week 7 live interaction session or the video or the course, we understood the difference between pyrolysis, gasification and combustion. So can anybody tell me what is the difference between this process? Like everything is going to at the end burn your biomass to give gaseous products. Of course the products will differ depending upon the process that we subject our biomass to, but all these processes are meant to heat the biomass. They are all thermal treatment. They just burn the biomass and then you will get the burnt product for your use. At that time the gas will be released, so that will be your biogas, that will be the so once you burn your biomass, you will be getting the heat energy released from that biomass and you will be using it for your application. So but there is significant difference between the three processes, your pyrolysis, gasification and combustion. So what is the difference? Can anybody tell me what is the difference between these three processes? Yes, anyone? This we discussed, and we have discussed twice this one, in week 7 as well as week 9 live interaction session. So the major difference between your pyrolysis, gasification and the combustion is the amount or the quantity of the oxygen getting involved in that process. So in case of pyrolysis, there is absolutely no oxygen is involved. So it's just burning of the biomass at a high temperature, and from there it will lead to some hydrocarbon product as well as the heat, and that heat will be used up for your application. In case of gasification, you use oxygen, but we use oxygen but we use limited amount of oxygen. And in case of combustion, we use either stoichiometric or excess quantity of oxygen so that complete combustion takes place. In case of gasification, since we limit the use of oxygen in our process, it's not necessary that the burning of the biomass is complete. So you cannot really get a complete combusted product. Like in case if you burn carbon with the excess of oxygen or stoichiometric quantity of oxygen, you will be getting CO2. Whereas if you do it with the limited quantity of oxygen, you will be getting carbon monoxide. So in gasification process we use a limited amount of supply of oxygen. So this gasification process is usually conducted or is usually done in kind of like how we do for a biogas digester. Here you have a gasifier. So gasifiers is basically the equipment where we do the gasification process. The biomass is burnt with the limited supply of oxygen and then the products are released out. So these are the three different types of gasifiers. So gasifiers primary classification is of two different types. One is your fixed type gasifiers and then the another one is the fluidized bed gasifiers. In the fixed bed gasifiers, it can be classified into three different types. One is your updraft gasifier, second one is your downdraft gasifier, and then the third one is your cross draft gasifier. Here in this live interaction session, we will focus only on these three. The fluidized bed gasifiers, you can always refer to the video lectures by Professor Vaibhav Vishant Gaut sir. So over there you can look up for the fluidized bed gasifiers. So in the fixed bed gasifiers, as I said, we have three different types as updraft, downdraft and crossdraft. The name itself, so the classification of these gasifiers of the fixed bed gasifier as up, down and cross is on the basis of the movement of your fuel and the gas. So if you first if you take in case of updraft gasifier, it is also called counterflow. So counterflow, so two things are flowing inside the system and those two are in the opposite direction. So that is the reason it is called counterflow gasifier. If you see in case of downdraft gasifier, it is also called concurrent gasifiers, or concurrent flow is happening inside the downdraft gasifiers. So here both the two like both the air as well as the gas, the fuel and the air are flowing in the same direction. So that is the reason why downdraft gasifier is also called concurrent gasifiers. If you see in case of cross draft, they both are flowing in the cross directions, like one in the perpendicular directions to each other. So based on the movement or based on the flow of your fuel, based on the direction of flow of the fuel and the air, the gasifiers, the fixed bed gasifiers can be classified as updraft, downdraft and cross draft gasifiers. So let me just write that. So the basis of the classification is basis of classification. The direction of flow of fuel and air. So in updraft gasifiers, the air as well as that so the air is entering from the bottom and the fuel is coming from the top. So since the motion, the direction of the air and the direction of the fuel is in the opposite direction, it is called as counterflow gasifiers. In downdraft, both the air as well as the fuel, the air is entering from the top to the bottom and the fuel is also entering from the top. Since the direction of both the air and the fuel is in the same direction, it is called as a concurrent flow gasifiers. In case of a cross draft gasifier, the direction of the flow of air and the direction of the flow of the fuel are perpendicular to each other. That is the reason it is called cross draft gasifiers. So let's just see one by one what is actually happening in the downdraft, updraft and cross draft gasifier. So first let us see about a downdraft gasifier. So as I said previously, it is called concurrent because the air is also entering from the top and the fuel is also entering from the top. So since the motion or the movement of air and the fuel is in the same direction, it is called concurrent. It is concurrent in operation, and the down word actually signifies the place from where the gas is actually taken out. So when once you burn the biomass, the product gas that gets generated has to be taken out of the gasifier. So in case of downdraft gasifier, it is taken from the bottom. So that is the reason it got mainly the name of downdraft gasifier. And yeah, so here what happens is the raw products, so your raw material, whatever the biomass that you are going to take, is passed through a high temperature zone. The reason why it is passed through the high temperature zone is because in the pyrolysis zone, the temperature is usually maintained only up to 350 degrees Celsius. So there can be some unburnt or unpyrolyzed product. So once it enters the combustion zone, due to the high temperature of approximately 400 to 650 or 750 degrees Celsius temperature is maintained in this combustion zone, due to which this pyrolyzed products are cracked and the gaseous hydrocarbon products are released. The heat from the combustion near to the air nozzle, so these are the air nozzles and this is the combustion zone where the material is burnt, and then the heat whatever is generated is transferred upwards by radiation and causes the pyrolysis. The heat sent upwards for the pyrolysis of the biomass results in the formation of carbon monoxide, carbon dioxide, hydrogen and water, and raises the temperature. After this combustion happens, this air actually goes and then your biomass material is burnt, the hot gas moves up, and then whatever the unburnt pyrolysis material is left, it gets cracked, and then that also come down and then get combusted, releasing the gases. The product gas enters into the reduction zone. So here what happens is the gas undergoes reduction reaction, and this reduction reaction generates products such as carbon monoxide, hydrogen gas as well as methane, and these gases are then taken out from this nozzle which is present at the bottom of the gasifier. So here the flow of the air and the flame direction are basically kept opposite to each other to maintain the homogeneous air gas flow rate. And this ash pit is used for whatever the combusted product, apart from the gas, if any kind of ash is generated. As such, we know when you burn a biomass, some amount of the inorganic constituent will be generated as ash. That ash is usually collected at the bottom of the gasifier. You can see even in the updraft also that provision is given everywhere. Updraft, downdraft and crossdraft, the ash pit is for collection of the inorganic constituents or the ash which gets generated by burning your biomass. So this is about the downdraft gasifier. Updraft gasifier, again the fuel comes from the top, air basically flows from the bottom, counterflow direction, and here the gas that gets generated by burning your biomass is collected at the top of your gasifier. So that is the reason it has the name updraft gasifier. So here the air actually enters, and then this entire gasifier is operated at a very high temperature. Combustion as well as the reduction zone are present near to the air nozzles. The exit gas, the air enters the combustion zone and is taken from the top. This updraft gasifier has a higher efficiency because the hot air passes through the fuel bed and leaves the gasifier at low temperatures. So higher amount of heat transfer usually takes place within this gasifier, and then the amount of ash compared to downdraft and crossdraft gasifier, whatever the amount of ash that gets generated will be very less. So this method is mostly suitable for high volatile feeds. Now coming to the crossdraft gasifier, here the air as well as the fuel enters in the perpendicular direction. both the combustion as well as the your reduction zone. This is your combustion zone and this is the reduction zone. If you see the picture, they are placed near to the air nozzle. The exit gas through this cross draft gasifier moves at a very high temperature, as well as the amount of CO2 that gets reduced. So the reduction reaction that happens here in case of a cross draft gasifier is very less. So the amount of carbon dioxide that is sent out of this gas is actually more. So the quality of the gas that gets generated is of low quality, and the efficiency, since the gas is actually coming out at a very high temperature, the efficiency is also low. So this cross draft gasifier is not suitable for application. So this is about the gasifiers. So main thing that you need to remember is the direct why it is called updraft downdraft, and how does the operation of counter flow and concurrent flow or cross current flow takes place. And in case of your updraft gasifier, since majority of the hydrocarbons is, or the biomass is converted into gas as well as the other reacted products, and the amount of ash that gets generated in the updraft gasifier is very less. So the ash generated in the updraft gasifier is very low compared to your downdraft gasifier. And here the gas that comes out of your updraft gasifier is of low temperature. So the efficiency of this process is very high of converting your biomass into the gaseous products. So updraft gasifier is something that is used predominantly compared to the other two types of gasifiers for the gasification of the biomass. Next we move on to pyrolysis. So pyrolysis, as I said, the biomass is actually burnt in the absence of oxygen. So here if you see the pyrolysis, this is a pyrolysis ternary diagram. So here we represent the component carbon, hydrogen and oxygen at the corners or the vertices of triangle, and the edges opposite to this corner. Let's say for example you take the oxygen corner, the edge opposite to this corner is the CH line, this line. I hope my diagram is visible to all of you. So this is this particular line. So the edge that is opposite to the vertices here, the concentration of that particular component is nil, is no component is actually present in this line. So for example, if you take for the CH line, the opposite corner is oxygen. So along this CH edge, if you see, the concentration of the oxygen or the products that gets produced has no oxygen present in them. Similarly, for if you take the edge opposite to the corner vertical opposite to the corner H, the CO line, here the concentration of the hydrogen is nil. And if you take the OH line, the opposite vertices is carbon, but if you see the OH line, the concentration of the carbon in this line or the products that gets generated and its carbon concentration is nil along this line. So the corner represents the pure components such as carbon, hydrogen and oxygen. The vertices represent the type of products that gets generated from the pyrolysis process, and that particular edge does not contain the component in the opposite vertices. So I hope you are able to understand. In case if you have doubts, then do let me know, because this might be a bit confusing. So if you take this vertices of oxygen and if you take the edge opposite to this vertices, that is your CH edge line, if you see the products in this particular line, the concentration of the oxygen or the presence of oxygen, the oxygen is not present, the presence of oxygen is almost nil. Similarly, this vertices is for hydrogen. If you take the opposite edge is CO line, so the concentration of hydrogen in the products along this line will be nil. Similarly, this is the carbon vertices, and the edge opposite to the carbon vertices is the OH line. Here the concentration of the carbon in the products will be nil. So that's how you can see. If you see for the vertices opposite to O, you have CH4, C2H4, char and coal. I mean, these are the gaseous products and these are the solid products inside your triangle and outside your triangle. If you see hydrogen, the opposite line is CO, and here it is only CO, carbon monoxide and carbon dioxide. And here opposite to carbon vertices is your OH line, and here only the H2O product is left out. And this, if you see this symbol F, H, S, O and P, this basically represents the hydrogen process, steam process, oxygen process, slow pyrolysis process and fast pyrolysis process. So slow pyrolysis process is nothing but it's a process where the pyrolysis of the biomass takes place at a lower temperature, let's say like around 400 degrees Celsius, and here the solid char products are usually produced. So slow pyrolysis basically takes a lot of time for the pyrolysis of the biomass to the formation of the product, or for the burning of the biomass to generate the heat, and it is usually carried out at a low temperature such as 400 degrees Celsius. So since it's carried out at a low temperature, the amount of time that requires for the burning of biomass will be more, and the product that gets released at the end of your slow pyrolysis process is nothing but is your solid char. So if you see here in this diagram, the biomass, when it undergoes the slow pyrolysis process, if you see the P line, it results in the formation of solid char. So that is something which is abundant in terms of carbon. So that is the reason it is present towards the vertices near to the carbon. If you see fast pyrolysis process, so in case of fast pyrolysis process, the temperature that the temperature at which your biomass is burned will be very high. So will be approximately around 1000 degrees Celsius. So since pyrolysis happens at such high temperature, so the amount of time that is required for the pyrolysis process will be very less. So here the biomass is heated rapidly, and then the heating rate is usually maintained around 1000 degree per Celsius. So you can 1000 degree Celsius per second. So you can understand the heating rate 1000 degree per Celsius, and the process is usually carried out at around 1000 degrees. So the pyrolysis process in case of fast pyrolysis happen in a very fractions of second. Yeah. And the products that gets generated out of your fast pyrolysis process is a high liquid products. And if you see F, so F is almost towards your carbon line. It is moving towards your hydrogen and away from the oxygen. So you can see the F is for fast pyrolysis. It is moving towards the carbon hydrogen line and very away from your oxygen line. So the products that gets released out of this fast pyrolysis process will be high volatile liquid products. So similarly, if you see for steam process, it will be moving towards your OH line, because in the steam process it basically results in the formation of steam. Steam is nothing but it mainly consists of a H2O, so it is moving towards the OH edge line. Hydrogen process, it results in the formation of hydrogen, so it is moving towards your hydrogen vertices. Oxygen process is something where your oxygen is getting released, so the process is moving towards your oxygen. So that's all with your pyrolysis ternary diagram. So if you have doubts, then please let me know, because this is quite not difficult, but yes, quite confusing to understand. If anybody have any doubts, then please let me know. does anybody have any doubt? So it's simple. If you know this diagram, if you have an understanding of the like if you just know, if you just see this diagram and think with of what you know about that process, then you will be able to understand. So if it is a slow pyrolysis process, low temperature process, it basically results in the formation of solid charge. So that's the reason the process is pointing towards your corners, which is your corner C. Similarly, fast pyrolysis process is moving towards your carbon hydrogen line and away from the oxygen line. So majority of the products that gets produced by a fast pyrolysis process will be having carbon and hydrogen in as a major constituent compared to oxygen. Similarly, in oxygen process, it will be majorly oxygen will be present in your product. Steam, it will be oxygen and hydrogen, so there will not be much amount of carbon. So that's the reason the arrow mark is pointing towards your OH edge line. And steam and if you see for hydrogen process, it's pointing towards your hydrogen corner, because majority will be your hydrogen that will get produced in the pyrolysis process. So by seeing the diagram, you can actually say what kind of products will be produced for this particular process, or if you know the process, then using the diagram you can say what will be the percentage of char, and yeah, like by knowing the process you can actually plot the diagram. So this is about the pyrolysis ternary diagram. If you have any doubts about the gasifier and pyrolysis ternary diagram, then do let me know. In case if you don't have any doubts, then we will move on towards solving some numerical problems. So in case if you have no doubts, then let's move towards this question. Let's just read the question. This question is very similar to what we did in the week 9 live interaction session, where we asked you to develop an equation for the combustion of propane, and over there also we had a theoretical air requirement and excess of air requirement. We asked you to calculate the air to fuel ratio. Here it's a similar question, but here we are focusing on the combustion of butane. So this is the question, and since we have done this previously and it's also solved in the video lecture in the course, I would like you to solve first before we discuss the solution here. So I'll just give you some time. You can solve the question and then let me know the answer, because this is what we previously did in our last week 9 live interaction also. So I'll just open that so that it will be easy for you. Yeah. So here if you see, we did it for the combustion of propane, and here we had two conditions. One is the theoretical air requirement and another one is the excess air. 30% of the excess air was used for the combustion of propane, and we were asked to calculate the operating air to fuel ratio of the system. So we developed first the combustion equation of how does our propane react with the oxygen, resulting in the formation of carbon dioxide and water. Then with respect to that, we developed two different equations. So the first equation, if you see, it is for theoretical air, or the amount of oxygen that is involved in your process will be stoichiometric, will be in stoichiometric quantity. So the exact quantity will be used, and in the second case you are going to use 30% of the excess air. So that we solved here. So since it's a 30% of the excess of air, we multiply that 30 percentage with the stoichiometric quantity of the air required, and then added that with the theoretical air requirement to get the total amount of air that is required for the burning of the propane, and from there we calculated the air to fuel ratio of the system. So here if you see the reason why, if you are able to recollect, the reason why we use the nitrogen is because the air has a significant portion of nitrogen present in it, so that will also be involved in the combustion process. But since the nitrogen is an inert gas, is a non-combustible gas, whatever the amount of nitrogen is involved in the reaction process will come out in the product as well. So if you see, the amount of nitrogen in the reactant side and the product side will be equal, because they will not react with your biomass and form products, so they will remain inert throughout the reaction process. And then we solved. So let's just have a quick recap of how we solved, so that it will be easy for you to solve the problem where we are going to involve the combustion of butane. So if you see, the first is basically exact quantity of air, and the second one is the excess quantity of air. So since excess amount of air is going to be used in the process, some amount of the oxygen will also be present in your reaction output, or the product side of your reaction. So we know that air consists of 79 percentage of nitrogen and 21 percentage of oxygen. So here we do not consider the contribution from the other type of gases that is present in the air. Since these two are predominantly present, the nitrogen and the oxygen, we will take only these two components for our calculation purposes. So 79 percentage of the nitrogen and 21 percentage of the oxygen. So for every mole of O2, there will be totally 3.76 mole of N2 is involved, 79 by 21, and this is going to react. So we develop this equation. So we just balance the number of carbon atoms on the reactant as well as that of the product side, and similarly we balanced all the atoms that are present on the reactants and the product side, and then we develop the equation. And then air to fuel theoretical ratio is nothing but mass of air by mass of fuel. I hope you are able to remember this formula. This is nothing but 4.76 times the number of oxygen, the number of moles of oxygen involved in the burning process, times your molecular weight of air by molecular weight of fuel. Molecular weight of air, we calculated, if you see this by this way, like, so 79 percentage of the total air is going to be nitrogen, so 0.79 times nitrogen mass, so N2. So nitrogen atoms weight, atomic weight is 14, so the molecular weight will be 28. And similarly for oxygen, atomic weight is 16 and molecular weight is 32. So we multiplied their molecular weight with their respective contributions, and then we calculated the molecular weight of air as 28.84 gram per mole. And similarly we calculated for propane. So propane is C3H8, atomic weight of carbon is 12, of hydrogen is 1, and from there you calculate the molecular weight of propane. The number of moles of oxygen that is involved in this process is 5, so we multiply that with 5, and then if you do the calculation, we got the air to fuel theoretical ratio as 15.5998 kg. Similarly we did for the excess of air requirement. So 30 percentage is present in excess. So with what is your theoretical quantity, we take 30 percentage of that and then add that to your theoretical quantity of air required, and then we develop the equation. Similarly here also we balance the carbon, hydrogen, oxygen and nitrogen atoms on either of your reactant and the product side, and from that we calculated the air to air fuel ratio of our system. So this was the procedure that we developed in the last week. Similarly, now you have to solve for this particular system of butane. So first we need to develop the equation for the butane, the combustion equation. Then after that we need to calculate the air to fuel ratio for the system. So butane formula is C4H10. I hope you are able to recollect that. So let's just solve that problem here. I hope, or otherwise you guys can also solve and then let me know the answer, because once you develop the equation it will be easy for you to do the calculation. So let me just write the equation here of what is the combustion of butane with oxygen. So butane is C4H10 plus, you have both your oxygen and nitrogen, and since here for the first case we are going to use the theoretical air, that is the exact stoichiometric quantity of air, so no O2 will be present on in your product side. So it will be only your carbon dioxide, water and your nitrogen, because the nitrogen is not going to react with the butane system. And now you need to balance this. So if you see, the number of atoms of carbon in your reactant side is 4, so in the product side also it should be 4. So here we can insert 4. So the total amount of hydrogen in your, so total number of atoms of hydrogen in your reactant side is 10, and since it is H2O, so the total atoms should be 10. In the product side also it is H2, so 5. So with this we can calculate the number of atoms of oxygen in your product side, and based on that you can balance it in your reactant side. So oxygen atom is totally 4, and since it's O2, so 4 times 2 will be 8, and here it will be 5, so 8 plus 5 is 13, and since it's already O2, so it will be 6.5, and nitrogen atoms will be 6.5 in the product side. So this is your equation. Oh sorry, 3.76. Because for every mole of O2, 3.76 mole of nitrogen is present in the air. So you need to take that also into consideration. So it will be 6.5 times 3.76. So let's just calculate what that will be. 6.5 times 3.76, 24.44. Let me just write this. This much amount of nitrogen will be present in your reactant and the product side. So now it's just about calculating your air to fuel ratio. Stoichio will be nothing but mass of your air, mass of fuel, and the formula is nothing but 4.76 times your N, that is N is nothing but the number of moles of air that is involved in the combustion process. So here the number of moles of air will be 6.5, so we insert 6.5 here, and molecular weight of air. So molecular weight of air, I am going to recalculate here. So it's 79% of nitrogen. Nitrogen's N2 gas molecular weight, nitrogen gas molecular weight is 28, plus 0.21, that is your oxygen contribution, and molecular weight of oxygen is 32. So if you do the calculation, oh sorry, it is 6.72 plus 22.12, 28.84 gram per mole. And what is the molecular weight of butane? Please let me know what is the molecular weight of butane. Yes, what is the molecular weight of butane? Yeah, what is the molecular weight of butane? It is C4H10, right? So molecular weight of butane will be 4 times atomic weight of carbon is 12 plus 10.
It is 58 to 1.
Yeah, it's 50. So you can take it as 58, for like, let's keep it as whole number. So 58 gram per mole. So for every 1 mole of butane you have totally, so the molecular weight is 58. So for 1 mole of butane there will be totally 58 grams. So now I think you can calculate the air to fuel stoichiometric ratio. So this will be 28.84 and that divided by 58. So what will be your answer, air to fuel for stoichiometry? It just, you need to do this multiplication. Yes, what will be the answer? What will be the air to fuel ratio, stoichiometric ratio? Yes, answers. Yeah, I need answers. What will be the answer for this? So it is nothing, it's just about multiplication. 4.76 times 6.5 times 28.84 and that divided by 58. So it will be nothing but 15.3846 kg of air per kg of fuel. because it's mass of air per mass of fuel, so it is kg of air per kg of fuel. So this is for the theoretical requirement or stoichiometric requirement of air. Like if you burn your butane in stoichiometric quantity of air, what will be the air to fuel ratio that will be required. But if you are going to do it in excess of air, the air to fuel ratio will change. So now we are supposed to calculate when you are going to burn your butane with a 40% excess of air. So here what is going to change is the amount of air, the value of n, and that will change your entire answer. So let me know what will be the equation for this system when you are going to use 40% excess of air. So you are going to use 40% excess of air in the system compared to your stoichiometric quantity of air that you used for the previous problem. So what will be the new equation? So it will be nothing but, so 6.5 times 6.5 moles of O2 of air is what you require, is what is your stoichiometric quantity, and you are going to have 40% excess of that. So as I said previously, it will be that stoichiometric quantity plus the 40% more of the stoichiometric quantity. So 40% of this will be nothing but 0.4 times 6.5. And what is 0.4 times 6.5? 2.6. So this much will be the excess of air which will be used in your system in addition to the stoichiometric quantity of air. So which means it will be 6. This much is your stoichiometric quantity, and to that you are going to add 40% more, so that will be this. So what will be the total? Yes, you just need to add that 6.5 and 2.6. So that will be 9.1 mole of air will be required. The 9.1 mole of air will be used for combustion of butane. If you are going to use 40% of excess or 40% more air compared to what is their stoichiometric quantity of air. So you now know the the number of moles of air required. So you have the equation C4H10 plus 9.1 moles of air is going to react with this. So for 1 mole of butane, 9.1 mole of air is going to react, and that is going to generate carbon dioxide plus water plus the excess of oxygen. If any oxygen is going to be present, that oxygen will be released out, and then your N2, which will be coming out as such as it entered without reacting. So you just need to balance this. So if you see, there are totally 4 carbon atoms in the reactant side, so it will be 4 on the product side also. You have to balance that, and number of hydrogen atoms is 10, so in the product side here it will be 5, so that will make up totally 10 hydrogen atoms. So and then nitrogen atoms will come out as such, so this will be 9.1 times 3.76. Now you just need to balance your oxygen. So in the reactant side, it will be the total number of oxygen atoms will be 9.1 times 2, that will be 18.2. In your product side, it will be 8 plus 5, that will be 13. So here you have totally 18.2, and here you have totally 13. So the amount of oxygen, like the number of the reactant side has approximately 5.2 atoms of oxygen less, so that will be coming here. So O2 is a molecule, so totally it will be 2.6. So this will make up totally 5.2 atoms of oxygen, and the equation will be balanced. I hope you know how to balance the equation, or you have learned how to balance this equation, because once you know how to balance the equation, then it's just about substituting in the formula. Everything else will remain the same except for the value of n. So that is very important here. You should know how to you should be proficient enough in balancing the equation to get the correct answer. So which means 9.1 mole of air will be participating in your combustion reaction. So air to fuel ratio will be nothing but, can you guys list calculate and let me know what will be the air to fuel ratio in this case when you use 40% of excess air? I have told everything, you just need to do the multiplication. Yes. A by air to fuel ratio for the system is required. What is it? Please let me know. So air to fuel ratio of your system is nothing but the mass of the air involved to the mass of the fuel used, and that is nothing but 4.76 times the number of moles of air used in the process, used in the combustion of the butane, times your molecular weight of air by molecular weight of your fuel. Molecular weight of air, you know, it is 28.84. Molecular weight of fuel, here fuel is nothing but butane, so butane's molecular weight we calculated as 58. So you know the molecular weight of fuel, you know the molecular weight of air, and you also know the number of molecules of air involved in the combustion process. So please let me know what is the air to fuel ratio of the system. It's just you need to know, do the multiplication. You know the number of moles of air that is involved in the combustion process. So 9.1 moles of air, of excess of air, or like 9.1 moles of air is involved in the combustion of your butane. So you know now your value of n. You let me know the answer. So it's just, let's calculate. Four 4.76 times 9.1 times your molecular weight of air, that is 28.84, and your molecular weight of fuel, that is your butane, which is 58. So let's calculate 4.76 times 9.1 times 28.84 divided by 58. So the answer is 21.538 kg of air per kg of fuel. So this much, this is your air to fuel ratio for the system that involves 40% of the excess of air for the combustion of butane. So we are done with doing these kind of questions on developing the equation for the combustion of any kind of hydrocarbon, and then calculating the air to fuel ratio for that system. We have solved two problems, and I hope you will be finding it easy and you can solve these type of questions comfortably and confidently whenever it is asked for you to solve, either in your assignment or in your exam. So now we move on towards our next question, which states that similar type of problem on calculating the air to fuel ratio and equivalence ratio. So here we are taking a natural gas, and then your natural gas is going to be fired in an industrial boiler. The process actually requires the oxygen concentration of 4 mole percent of flue gas. They are asking you to calculate the air to fuel and the equivalence ratio. So here you know the oxygen concentration, but then the oxygen concentration is given in terms of mole percentage of your flue gas. It's not directly given like theoretical air requirement or excess of air requirement, but it is given in terms of mole percent. So you are supposed to use this information to calculate the two parameters, and you can assume here that your natural gas is nothing but natural gas consists of methane. Natural gas is methane. For solving purpose, we take natural gas as the methane. So again, very similar, you need to develop the equation and then solve the problem. So since we now know how to develop the equation from our previous live interaction session and also from today's live interaction session, I require you to write the equation and then let me know for methane, for the combustion of methane. For combustion of methane, CH4. You write the combustion equation of methane and then tell me. Your flue gas is nothing but the gas that is actually coming out in the product side. So that is what is the flue gas. So for the time being, I want to know what is the combustion equation for the process. Just a skeletal equation would be enough. So it is nothing but CH4 plus your air, that is oxygen and nitrogen. And since here we do not know whether they are going to supply us with an excess of air or whether it's just a theoretical quantity of air, here we just know that the concentration is 4 mole percentage of flue gas. So let's just consider a moles of air is going to react with your methane and then form the products. So that will be CO2 plus H2O. And since we are not aware of whether it is stoichiometric quantity of air is going to be involved in the process or theoretical quantity of air is going to be, or excess of air is going to be involved in the process, so we for the safety purpose we just write O2 in the product side also, plus the nitrogen gas that will be coming out of the system. So here if you see, you can actually balance the hydrogen atoms, you can also balance the carbon atoms, that will be 1. Now you just need to balance your oxygen atoms. Nitrogen atoms will be 3.76 times A, and you do not know how much amount of the O2 is going to come out in your product side. It can be any value, B can be also 0, it can also be 0. So you don't know, so you give a variable B. Now we do not know how much amount of the oxygen is going to be involved in the process or air is going to be fed into your system for the burning of methane, but what we know is the concentration of the oxygen in your flue gas. So the flue gas, as I said, is your gas that is generating out of the system as products. So over there the mole percentage of the oxygen is 4 mole percent. So with this we can calculate the value of B. So mole percentage is nothing but the moles of that particular component to the total number of the moles of the flue gas. So here mole percentage of oxygen is 4%. So mole percent of O2 is 4% or 0.04. This is nothing but the number of moles of O2 in your flue gas to the total number of moles of your flue gas. Is equal to number of moles of O2 in the flue gas by the total number of moles in your flue gas. Total number of moles product, total number of moles of product in the flue gas. So mole percentage of O2 in the flue gas is 0.04. Number of moles of O2 in the flue gas, if you see here, we have taken a variable B, so we can write B divided by total number of moles of O2, total number of moles of product in the flue gas. So mole percent is nothing but number of moles of that particular component to the total number of moles in the product. So total number of moles in the product will be 1 mole from CO2, 2 moles from water, and again B moles from O2, because since you are calculating the total number of moles of O2 in the total number of moles in the product side, you need to also take into account the number of moles of O2 here, plus 3.76 times A, right? So you can now calculate the relationship. 0.04 is nothing but B divided by 3 plus B plus 3.67 times A. Now we need to see get a relationship between B and A, because here you have one equation but two variables, so you cannot solve. So we need another relationship, or a relationship between B and A, so that we can solve this equation. If you see, this equation is not balanced yet. The total number of moles total number of atoms of oxygen in the reactant side and the total number of oxygen in the product side should be balanced, right? So total number of oxygen atoms in the reactant side is 2A. In the product side will be from carbon dioxide it will be 2, from water it will be 2 plus 2B. So the number of moles of O2 has to be balanced in the equation. So from here we can actually get a relationship between B and A. So this is nothing but A equal to 2 plus B. So B is nothing but 2 minus, A minus 2. So now you have one equation. This equation is with respect to our given data that says that the oxygen concentration in your flue gas is 4 mole percent. So we express that mole percentage as number of moles of O2 in the flue gas to the total number of moles of product in the flue gas, and then we balance our equation for the carbon, hydrogen, oxygen and nitrogen atoms, and then we get a relationship as B equals to A minus 2. This is your second equation. Now using two equation, you have two unknown variables and two unknown equations, so you can solve for both the variables. So substitute 2 in 1, 2 in so that will be 0.04 equals to, here B is nothing but A minus 2, so A minus 2 divided by 3 plus A minus 2 again plus 3.76A. So that will be A minus 2 divided by 3 minus 2 will be 1 plus A plus 3.76A will be 4.76A. So now you need to solve the equation and get the value of A. So do let me know what will be the value of A. It just you need to cross multiply and then get the value of A. So 0.04 equals to A minus 2 divided by 1 plus 4.76A. So if you cross multiply this, yeah, if you cross multiply this, you will be getting is equal to A minus 2. So just open the bracket, we take the variables to the right hand side and then your numericals to the left hand side. So it will be A minus 0.04 times 4.76. So it will be 2.04 equals to 0.04 times 4.76. 0.1904. 1 minus 0.1904 times A. So the value of A will be 2.04 divided by what is 1 minus 0.1904. 1 minus 0.1904 is 0.8096. So that will be 2.04 divided by 0.8096, which will be 2.519 or 2.52 you can take. So this is your value of A. Now you know your value of A, so that means you know your number of moles that is involved for the combustion of methane. From this you can calculate the air to fuel ratio for the system. So calculate this and then let me know the answer. Please let me know the answer. I'll just come back. I need to take some water. So in the meantime, please calculate the air to fuel ratio for your system. So yes, what is the air to fuel ratio for the system? Anyone? Okay, so let's just calculate that value. So now here you know the value of A. So A is nothing but the number of moles of air that is involved in the process. So which will be air to fuel ratio of the system is nothing but mass of your air to the mass of the fuel. So that is equal to 4.76 times the number of moles of air that is involved in the process. So A value is 2.52 we calculated, that is your number of moles of O2 that is, or of air that is involved in the process, times 28.84 divided by methane's molecular weight is CH4, so 12 plus 4, that is 16. So what will be the answer for this? Let's just calculate. So 21.6213 is the answer. Kg of air per kg of fuel. So the air to fuel ratio for your operating system is 21.65 kg of air per kg of fuel if you use 2.52 moles of air for the combustion of methane. Now we are also asked to calculate the equivalence ratio of your system. So what is the definition of the equivalence ratio? So if you remember, the equivalence ratio is defined as the ratio of the air to the fuel ratio, or the stoichiometric air to the fuel ratio to the air to fuel ratio of your system, right? So it is, what is your equivalence ratio? Equivalence ratio is nothing but air to fuel ratio, the stoichiometric air to fuel ratio stoichio divided by the air to fuel ratio of your system, that is the operating system in operation. So in operation we know the air to fuel ratio is 21.65 kg of air per kg of fuel, but to calculate the equivalent ratio you need to know what is the air to the stoichiometric air to fuel ratio for your system. So for that we need to again develop that equation and then calculate the air to fuel ratio stoichiometry, and from there we will be able to calculate the equivalent ratios. So we need to know how much amount of moles of air will be used, or like how many, or what is the stoichiometric moles of air will be required for our process, right? So that will be CH4 plus O2 plus 3.76 N2 since we know we are just going to use stoichiometric quantity of air, so there will be no excess of oxygen that will be coming out of your system in the product side as a product. So here again we need to balance the carbon, hydrogen, oxygen and nitrogen atoms. So 2 and 2 will make 4. So carbon and hydrogen atoms are both balanced. If you see the oxygen atom total is 4 here, so it will be 2 and this will be 3.76 times 2. So to calculate the equivalence ratio, you require the stoichiometric air to fuel ratio and your air to fuel ratio of your operating system. So we have calculated previously the air to fuel operating system ratio, air to fuel ratio in your operating system. Now we need to calculate the air to fuel ratio stoichiometry. So for that we are going to again develop the equation with the stoichiometric quantity of air. So that is this equation. So 2 moles of air is involved in this process. So air to fuel stoichiometry will be 4.76 times n. N is 2. Molecular weight of air is 28.84 divided by molecular weight of fuel, that is your methane. Methane's molecular weight is 16. So we need to calculate this. So 4.76 times 2 times 28.84 divided by 16, that is 17.1598. Similarly, kg per kg. Now we need to calculate the equivalence ratio. So that is nothing but the stoichiometric air to fuel ratio, that is 17.1598 divided by the air to fuel ratio of your operating system, that we got as 21.653. So your equivalence ratio will be 17.1598 divided by 21.653, 0.792. This is your equivalence ratio. So this is how you calculate your equivalence ratio. So when you are asked to calculate the equivalent ratio, then you are supposed to calculate both the stoichiometric air to fuel ratio and the air to fuel ratio of the operating system as per the question, and then you need to divide the stoichiometric air to fuel ratio and the air to fuel ratio of your operating system to get the equivalence ratio. So similarly, if you see for this question also, we can calculate the equivalence ratio. So it will be nothing but the stoichiometric value is, where is it, 15.3846. This is for the previous problem. If you remember, over there we didn't calculate the equivalence ratio, so we are calculating it now. And air to fuel ratio of the operating system as per the question is 21.538. So the value will be, what is the value, 15.3846 divided by 21.536, 0.7143. 0.7143. So the equivalence ratio for our previous problem is 0.7143 and for this problem is 0.792. So this is how you develop an equation, calculate the stoichiometric air to fuel ratio of your operating system, and then its equivalence ratio. So similarly, we have another one question, but this is a very simple question compared to what we have done previously, and this is a very straightforward question also. So here it is in 2 parts, and these 2 parts do not have any interdependency. The first part says that your equivalence ratio is 0.6 and is asking you to determine the air to fuel ratio for a ethane gas, operating air to fuel ratio for your ethane gas. Second part, it gives your air to fuel mixture or air to fuel ratio as 18:1, and they are asking you to calculate the equivalence ratio. So instead of asking you to develop an equation and then asking you to calculate all the parameters, one parameter is given to you, you are asked to calculate the other parameter, its interdependent parameter. So compared to previous two questions, this question is quite simple. So for the first question, again, since you are given the equivalence ratio and they are asking you the air to fuel ratio of a system, you have to calculate the air to fuel stoichiometry first, stoichiometric air to fuel ratio. Once you calculate that, you know your equivalence ratio, you know your stoichiometric air to fuel ratio, so you will be able to calculate your air to fuel ratio of your system. Second one, over there you know your air to fuel ratio of your system, you know the combustion equation for propane, so you will be able to calculate the stoichiometric air to fuel ratio. So then with these two you can calculate the equivalence ratio. So it's just that you need to use that one formula. Equivalence ratio is A upon F stoichiometry to A upon F of the operating system, and then you will be able to calculate. So yeah, I think I'll just give you the equation and you can calculate it later or take it as a home task, because once you know the equation, I hope you will be able to solve the questions, both of them. So ethane formula is C2H6, right? And here we are supposed to know the the stoichiometric air to fuel ratio. So we take stoichiometric quantity of air for the burning of our ethane gas. So which means we do not have any excess of oxygen that will be releasing out of the system. So it will be just CO2 plus H2O plus your unreacted nitrogen gas that will be coming out of the system. So now you need to balance the equation. So it will be 2 moles of CO2, here it will be 3 moles of water. So the total number of oxygen atom will be 4 plus 3, that will be 7. So here it will be 3.5, and nitrogen atoms will be 3.5 times 3.76. Yeah. So since you know this, you can calculate the stoichiometric air to fuel ratio as 4.76 times 3.5 times air is 28.84, this remains constant, and molecular weight of your fuel is the ethane molecular weight, so that will be 24 plus 6, so 30. Three times 3.5 times 28.84 divided by 30, 16.015. So if you know your stoichiometric air to fuel ratio, now you have your equivalence ratio given to you. So once you know both of them, you will be able to calculate your air to fuel ratio for the system. Is nothing but air to fuel, the stoichiometric air to fuel ratio divided by your equivalence ratio. So that will be 16.015 divided by 0.6. That is 26.69. kg of air per kg of fuel. It is important to know the units for this parameter. So now you know how to solve one. I hope you will be able to solve the B part also on your own. You can take this as a home task. You can, it is similar, it is very similar. You need to develop a equation which involves stoichiometric quantity of air. You need to develop an equation, get the number of moles of air that will be required for burning of your propane. Once you know the number of moles of air that will be required for burning of your propane, you will be able to calculate your air to fuel stoichiometric air to fuel ratio. And once you know that, you have your air to fuel mixture ratio for your operating system, so then you will be able to calculate your equivalence ratio. So yeah, we end our discussion on air to fuel ratio and your equivalence ratio here. So we have approximately solved, if I am not wrong, 5 problems, including what we covered in the last live interaction session. So yeah, I hope you will be able to comfortably solve this now. Now let's, in case if you have any doubts in this, please let me know now, so that we can have a discussion over this before we move on to our next 2 questions. Yes, does anybody have any doubt? Meanwhile, let me just write the steps for this. Steps for the calculation. So first is develop the combustion equation. If you have any doubts, please let me know in the meantime. Develop the combustion equation. Balance the combustion equation. Once the balance is done, identify the number of moles of air that is involved in the process, that is involved in the combustion process of the hydrocarbon or your biomass. Now once you know the number of moles of air, calculate your air to fuel ratio, stoichiometry, with the formula, with the above mentioned formula. So once you know this, depending upon the parameters what is asked in the question, you will be able to solve for whatever they have asked. Either let it be the air to fuel ratio of your system by giving you the equivalence ratio, or by giving you the air to fuel ratio of your operating system and asking you your equivalence ratio. So these 4 steps will be similar for every problem that you take, and then rest will depend upon the question that you are going to solve. So if you don't have any doubt, then let's move on towards the next question. So here it states that a gasifier is used, okay, and it's producing syngas, and that syngas is produced at a rate of 0.26 kilomole per kg of feed, and the volumetric composition of the syngas is given as carbon dioxide, methane, hydrogen and nitrogen. Now they are asking you to calculate the heating value of your syngas, and then they have given you the heats of combustion of different gases also. So here you are asked to calculate the heating value. So it's very simple. Let's solve. So your syngas has the following composition. So 27.5 percentage of carbon monoxide, 5 percentage of methane, and 15 percentage of hydrogen gas. Nitrogen we usually don't take it into account because they will not since they are inert and incombustible, so they will not be adding any heating value to your syngas system. So that part, whatever is dedicated for the nitrogen, can be neglected because it does not undergo combustion. It's not a combustible gas. So we have this, we are given the heat of combustion values, and then they are asking you the heating value of the syngas, and it's also given that the syngas is produced at a rate of 0.265 kilomole per kg of feed. So what it means? So for 1 kg of feed you have 0.265 kilomole or 265 moles of syngas is produced, right? Yeah, this is what is the meaning. So for every 1 kg of the feed that you are going to feed into your gasifier, 265 moles or 0.265 kilomoles of the syngas is going to come out. Now here the composition that we have for the syngas is a volumetric composition. It's not based on number of moles or based on the mass. It is based on the volume. Basis is volume. So you cannot just use the 265 and then find out the contribution from each of them, because since the composition of your syngas is in terms of volume, so you cannot just directly use the number of moles of the syngas and then find out the heating value. You need to convert the number of moles into their volume percentage and then calculate the heat of combustion. So how to convert the moles into volume? So if you know, I hope you will be able to recollect, 1 mole occupies 22.4 liters of gas at STP condition. Right? I hope you will be able to remember. So which means in terms of meter cube, 1 mole will be able to occupy 0.0224 meter cube of gas at STP, because 1 meter cube is equal to 1000 liters. So 1 liter will be equal to 10 power minus 3 meter cube, and if you multiply with this, you will be getting 1 mole is 1 mole of 1 mole gas will occupy 0.0224 meter cube of space. So this is for 1 mole. For 265 moles, what will be the volume? So that will be 0.0224 times 265. So let's calculate 0.0224 times 265. That is nothing but 5.936. 5.936 meter cube of syngas per kg of feed. So this much meter cube of syngas per kg of feed is going to be produced, and out of this particular 5.936 meter cube, 27.5 is from carbon monoxide, 5% is from your methane, and 15% is from your hydrogen gas. So we need to calculate what is the percentage, or what is or how much volume is occupied by these different gases. So for carbon monoxide, if you take, it will be it is written, it is given as 27.5%, right? So 27.5 divided by 100 times 5.936. Similarly for methane it will be 5%, so 5 by 100 times 5.936. Similarly for hydrogen gas it will be 15 by 100 times 5.936. so we need to calculate what is the contribution from each gas. So 0.275 times 5.936 is 1.6324 meter cube. I am writing it as 0.275 because 27.5 by 100 is nothing but 0.275. Next, for methane it will be 0.5936 times 5 by 100, so that will be 0.05, 0.2968 meter cube. Now for hydrogen gas it is 5.936 times 15%, 15 by 100, so 0.15, 0.8904 meter cube. This is the contribution from each of the gas. So this particular amount of meter cube times the heat of combustion of that particular gas will give you the heating value of the syngas. So heating value of syngas is nothing but the volume of the particular gas times the heat of combustion of that gas of combustion. So what will be the value? So you just need to multiply for each and every different gas that is a constituent of your syngas. So this is nothing but, so for first we take for carbon monoxide, so it will be 1.6324 meter cube times the heat of combustion of carbon monoxide is 12.6 megajoules per meter cube. This is for carbon monoxide. Similarly for methane also we have to add this with the contribution from methane as well as hydrogen. So what will be the contribution from methane? So that will be 0.2968. Let me write the units at the end. Times, what is the heat of combustion of methane? 39.8 megajoules per meter cube, plus now for hydrogen gas, so 0.8904 times heat of combustion of hydrogen is 12.7 megajoules per meter cube. So meter cube times megajoules per meter cube. So meter cube will get cancelled, so it will be only in terms of megajoules. So heating value will be, you need to multiply each one of them, 1.6324 times 12.6, 20.568 plus 0.2968 times 39.8, that will be 11.81 plus 0.8094 times heat of combustion of hydrogen gas is 12.7, 10.279. So if you add all of them, 20.568 plus 11.81 plus 10.279. 42.657 megajoules. So the heating value of your syngas is nothing but 42.657 megajoules. So this is how you will calculate if you are asked to calculate the heating value of the syngas. If your composition for the syngas is given either in terms of mole percent or mass percent, and then your syngas is also produced at this much amount of kilomole per kg of feed, then you can just directly find out the contribution by multiplying the percentage times how much amount of syngas is getting produced. But if it in case is asked in terms of either mass composition or volumetric composition, then you need to convert convert the amount of syngas produced from the number of moles to either mass or in terms of volume, in terms of mass or in terms of volume, and then calculate their contributions. After calculating the contribution, you multiply that with the heat of combustion of that particular gas and then sum it up to get the heating value of your syngas. So here the difference is that like what makes this question a bit tricky is that the composition of your syngas is given in terms of volumes and not in terms of moles. So that is the trick here. So you need to be very careful while reading the question, or otherwise the chances of making mistakes could be more in this case. So we have a question, one more question, and I guess we have like approximately 10 minutes left. So let's solve this question also before we conclude our session for today. So here, I hope you have no doubts with respect to the previous question. If you have any doubts, please let me know. So let me just read this question. Your biomass gasifier is used to power a compression engine, and they are operating in a dual fuel mode with 75% diesel replacement, and they have given your biomass feed rate as 450 kg per hour. They are asking you to calculate the amount of power required. The engine efficiency is given as 30%, gasifier efficiency is given as 65%, and now they are asking you to calculate the power required from the system, power required to run your compression engine. They have given your calorific value as 17,500 kilojoule per kg of biomass. So this is very similar to what you would have also seen in the NPTEL course. We are just going to solve one similar problem here also for practice purpose. So how do you go about calculating the power that will be required for running your compression engine? Your biomass feed rate is known, so from here you need to calculate the power required. So let's just start solving the problem. So since your biomass feed rate is known, you will be able to calculate the power that will be generated by burning this biomass. So the biomass feed rate is 450 kilogram per hour, kg per hour, and you know your calorific value of the biomass as 17,500 kilojoule per kg. So the input power, yes, do you have any doubts? Hello? Okay, yeah.
No, sir.
Oh, okay, yeah, fine. So let's just finish this question. So input power will be nothing but your biomass feed rate times your calorific value. So that will be input power will be nothing but your biomass feed rate is 450 times your calorific value is 17,500. Units will be kg per hour times your calorific value units is kilojoules per kg. So the kg will get cancelled and you will be getting 450 times 17,500, 7875,000 kilojoule per hour. So let's convert the input power in terms of watts. So you know 1 watt is nothing but 1 joule per second. So if you have to calculate this kilojoule per hour to kilowatts, it will be 1 kilowatt is 1 kilojoules per second, but here it is given in terms of hours. So you are supposed to convert the hour into seconds and then proceed further. So 787500 in 1 hour, there are totally 3600 seconds in 1 hour, so we just divide that. So what will be your input power? 787500 divided by 3600, 2187.5 kilowatt. So the input power will be 2187.5. Now the gasifier has a particular efficiency of 65%. So it is not that the entire energy will be used up for the compression engine. 65% is only what is going to be used up. The rest 35% will be going out as a loss. So output from so your output from gasifier is nothing but 0.65 times 2187.5. The reason why we are giving 0.65 is because the gasifier efficiency is 65%. So 2187.5 times 0.65, that will be 1421.875 kilowatt. So this will be the output from the gasifier and this will be fed into your engine. So the engine has 75% of diesel replacement. So 0.75 times of your total power is this 1421.875 kilowatt. So whatever the amount of energy or the power that is basically coming out from your gasifier will be fed into the engine. Since the engine has a diesel replacement of 75%, we write so that 75% of the power is nothing but this the incoming power from your gasifier. So the total power of your engine system will be so this will be the total power to your engine system, 1421.875 divided by 1421.875 divided by 0.75, 1895.833 kilowatt. Now the engine itself has a particular efficiency of 30%. So engine efficiency is 30%, or that is nothing but 0.3. So you need to multiply this total power that is supplied to your engine times this 0.3, the efficiency. So that will be nothing but 0.3 times 1895.833. So what will be that? 568.7499 kilowatt. So this will be the power required for running your compression engine. So first your biomass is fed into your gasifier at a particular feed rate. That will be that will basically release energy. So that power that is released from your biomass is nothing but 2187.5 kilowatt. This will be your output from the gasifier. This will be the amount of energy that will be generated in your gasifier. Since the gasifier efficiency is not 100%, it's only 65%. So the output from your gasifier is nothing but the gasifier efficiency 0.65 times the power that is generated from burning your biomass. So it will be 1421.875 kilowatt, and this is now fed into your engine. Since the engine has a 75% diesel replacement, so you need to calculate the total power that will be supplied to the engine. That will be 1895.833. Since the engine has only 30% efficiency, so 30% of this value will be the power that will be used to run your compression engine. So yeah, I hope you understood this. In case if you have any doubts, then let me know. If you have any doubts either with this question or with any other question or concepts that we discussed for today. Do you have any doubts? Like that's all for today. Only those 5 questions. So let me just stop presenting my screen. So if you have any doubts, then please let me know, or otherwise we can conclude our session for today. So yeah, I think we can conclude our session for today if you guys have no doubts. So thank you everyone for joining today's session. All the lectures, the videos and the presentations will be available to you in the NPTEL portal. If you scroll down in your course page, left hand side at the bottom, you will see problem solving session. If you click on that, you will be redirected to a Google Sheet from where you can access the recording for the live interaction session as well as the presentation. It is also uploaded in the YouTube channel. So thank you for joining today's session. Let's meet next week for our week 11 live interaction session. That will be on 7th April 2024, same 5 p.m. to 7 p.m. I would like to thank both Professor Vaibhav Vishant Gaut sir, Ananda Lakshmi ma'am, as well as the NPTEL team for providing me this opportunity to interact with you all on this in this Sunday afternoon. So thank you. In case if you have any doubts, please email me. I will be able to respond to you as soon as possible. So yeah, in case if you have any doubts, then let's conclude the session. Thank you and have a happy weekend.